And thank you for having me here once more. Yeah, so I'll try to share a bit our experience with fuzzing in particular. And the main concept is not really explaining that much what we did and why we did it and things like this, but more share our experience so that if you are in the same boat as we are, you have some pointers about how to do pretty much the same things and do it properly. So a very quick, fuzzy introduction, of course, considering the context. I got my PhD at the University of Napoli, and with other colleagues there, I founded a company that is called Meetecho, or Meetecho as it should be called. You have some pointers there, some previous presentations, including some presentations I did here at Kamailio. And very few words on Meetecho. It's a very small company. We do the usual things that you can expect out of a company like ours, so consulting, support, licensing, and things like this. And we are based in the south of Italy, especially Napoli, which looks pretty much like this. So quite a nice view. And don't forget that castle over there, because it will come back before the end of this presentation in one form or another. So first of all, it's me talking about all this, but I should actually give the proper credit to Alessandro Toppi, who is my colleague, who actually worked on most of these, actually almost all of this stuff. He actually introduced some of the concept already at Fuzz, so it was a really good introduction for the talk that I'm going to give here. Luckily for him, though, he just got married last week, so it's halfway around Japan right now with his lovely wife, so having fun. So kudos to him for all this job. And talking about fuzzing, it shouldn't really be new to Kamailio, because I mean, just last year we had a couple of very interesting presentations, one by Henning that you can see over there, and another from Sandro, who presented something yesterday as well. And they did some very good talks on different aspects of how to actually fuzz RTC systems, more or less tailored for Kamailio and on SIP in general. And I just watched them again before actually working on my presentations, and I was surprised that I didn't actually, let's say, invest more time on that, because they actually should have scared me a year ago. Instead, we waited way too much for that. And more precisely, there were some blog posts by Google recently, especially by the Google Project Zero, which is a team of security analysts at Google, who basically started working on, let's say, focusing on video conferencing applications of different sorts. So they started writing tooling applications and stuff like this, malicious endpoints generating the usual randomized input and so on, just to try and figure out if they could break the existing and widespread conferencing applications out there, how easy it would be and so on. And it turned out that it was quite easy. So apart from some effort on working on the tooling, of course, which took them some time, they actually managed to break some very popular applications like Apple FaceTime, WhatsApp, but most importantly for us, WebRTC as well. So they found a lot of issues there, which, of course, luckily, the Google Chrome team acted fastly upon, and so they managed to implement fuzzing properly quite fast in their own application. But of course, it left all of us, others working with WebRTC, a bit scared with that. And most importantly, the real wake-up call came from a blog post on the WebRTC Hacks blog, which is actually quite popular if you're WebRTC, where Philip Panke actually showed how it was really easy to do some very simple testing experiments, and of course, we chose Janus to crash as a sample to crash everything. And so he showed how using a very simple RTCP message, you could actually bring down the functions that we had done for the purpose, which of course, as you can expect, scared us quite a lot. And so we started investigating what we could do with respect to that. And we've seen from the previous presentations that the talks by Henning and Sandro were, in their context, more specific on the SIP and SDP signaling, which were helpful, and of course we took advantage of some of those concepts, but with respect to WebRTC, were less useful than we actually needed. And so, most importantly, we needed something that was more specific to WebRTC itself, which is signal agnostic, so SIP is not really relevant to Janus in our context, even though we do use SDP. But there are actually other protocols that we do need to worry about. So anything that involves not traversal, which means all the ICE stack, STAN, Turnbull protocols that can be actually subject to attacks of one way or another, the DTLS handshake in order to create your secure context, or the SRTP context for RTP, of course, their payloads and stuff like this. And payloads are actually quite important, and RTP payloads are actually very important, because even RTP payloads, which in theory should be pretty much opaque to the application, can actually introduce issues when you start using them. For instance, to detect the video resolution without decoding anything, or identifying layers, temporal layers, and stuff like this when doing simulcast. So we were pretty scared at that point, considering how many things can break at the same time. And so we started investigating a bit what fuzzing is. And basically, just not to go too much into it, especially because we had already a very good introduction last year on that, you can see it as an automated software testing technique of some sort, where basically you provide invalid value of some sort to a program, and you see what happens. So your functions have been built in order to parse some fields, some protocols, something, and so on and so forth. And if something changes there and it causes your functions to crash, you have something to fix, of course, because you cannot always assume that what you get is actually a valid message of that specific protocol, which means that the typical flow, I mean, this is not specific. I mean, it's specific to some form of fuzzing, but the typical workflow is you have an engine that generates inputs repeatedly. Each time the input is basically mutated depending on an existing subset. So let's say you have some valid RTP packets. These packets can be mutated somehow before they are fed to your application, so that they are, let's say, they look like valid RTP packets, but there is something wrong in them that may confuse your parser. Then this input data is, of course, parsed to your target function, so whatever you want to be monitored, then, of course, you are supposed to monitor these functions in order to make sure that you don't have leaks, that you are not causing overflows when reading stuff, and so on and so forth. Anytime a new iteration completes, basically you have some updated coverage of which parts of your code have actually been investigated, because, of course, if these only triggers some parts of your code and not others, you know that some parts of the code are robust, you know nothing about other parts of the code. So the idea is that hopefully as much as possible of your code that handles these protocols is actually covered, so that you are safer with respect to that. And the idea is that this actually repeats ad libitum, so until it crashes, or hopefully until you just press Control-C to stop everything. And of course, repeatability is actually very important, because if it crashes, most of the tools, and the one that we used as well in particular, do preserve the actual message that caused your application to crash, which means that then you can focus exactly on that. So not on doing the repeated tests, so on and so forth, but just focus on exactly what caused your program to crash, fix that, try again, and fix everything that way. Which brings us to Janus. So as Daniel introduced, our component is a general purpose and completely open source WebRTC server. You can find some pointers there, including demos, community, and so on. And the way it is worked, it basically implements the WebRTC stack in its core, which means that all of those protocols that I introduced before are actually part of the Janus core functionality. And then everything else is basically a module. So the application level transports for the Janus API are different plugins that you can plug. And same thing for the actual application logic. So we have a conferencing plugin, a plugin to talk to the SIP world, a plugin to do broadcasting and stuff like this. These plugins receive the media that is decapsulated from all the WebRTC stuff and just work on it in order to route it or bridge it, mix it, or whatever needs to be done, which can, of course, then be composed in different things, in different ways in order to build complex applications. I mean, all of this is not important for the purpose of this presentation, if not for the fact that our WebRTC stack is completely in the core, which means that this is where we've started to focus everything. So working on plugins will be probably important later on, but what we really wanted to focus on at this point was the WebRTC stack, so making sure that nothing can break just because of packets we receive on that end. And I mean, just looking at how Janus is built, the dependencies it has, and so on, we had at least some good news in the sense that most of the dependencies that we use are already fuzzed on their own. So for instance, we use libnice for all the ICE stack, and they have their own fuzzing mechanisms that actually takes care of all of that. So at least in principle, we shouldn't worry about that, or at least if there were an issue, it should be solved there rather than in Janus, because we never see a stun packet ourselves in the application. Same thing for DTLS, because of course there it's the OpenSSL or any related family that does that. libsRTP is also very good in fuzzing the secure aspects of the encryption parts of the RTP, and same thing for SCTP, which is used for data channels. There may be other dependencies that may need fuzzing. I mean, I haven't investigated much, mostly with respect to transports or JSON support. Actually, JSON support, I tried to fuzz a bit. I didn't find any issue, but I'll probably come back to that later on. Others were done by me, or at least by us, so they definitely needed fuzzing because I don't trust my code, so nobody should trust their own code. So, and in fact, it was most importantly the RTCP parsing, RTP processing, so any kind of extensions or code-specific payloads, so anything that actually traverses an existing packet to do some elaboration, and also SDP parsing and processing, which we rewrote ourselves for our own needs. Which leads us to libfuzzer, which is the tool that we chose for the purpose. And it's actually a very good and effective tool that really helped us a lot in the process. And it's coverage guided, which again brings us back to what I was saying before. You want to be able to be sure that most parts of your code are actually evaluated when you do all of this fuzzing and not just parts of them, because you want to be sure that everything is covered. It's used by a lot of well-known applications, some of the usual suspects and so on, and so it definitely made sense for us to trust what they were doing as well. And some of its characteristics are that, first of all, you need to compile your sources with Clang, which, if you followed Sandro's presentation yesterday, is already a very important step. So if your application doesn't compile with Clang, you already have something wrong that you need to fix. And so you have to do that. And as an additional value, as we'll see later, it also gives us some more feedback about things you may need to fix that you weren't even aware of. It works in process, which means that it does need to be linked with the application under test. And as we'll see later, this required some effort on our side because, of course, Janus is not a library. It's an application. It has its own main and so on, while libfuzzer tries to take control of that. So you have to actually rework some of the aspects in order to do everything. Basically, it feeds inputs to the target via a so-called fuzzing entry point, and we'll see this in a subsequent example because it will be clearer that way. And most importantly, every step of the process is actually monitored through the sanitizer tools like libazan or leak sanitizer and stuff like that are all part of the LLVM project that you see over there and that Clang facilitates. So basically, you can see this as an iterative process that works that way. So you have, again, you execute, you have the fuzzing engine generating data, you execute the fuzzing target, so whatever your functions are that should elaborate the data, see what happens, update the code coverage, update the corpus, with, which is basically the data that you have already evaluated somehow, and you don't have to go back, repeat, and so on and so forth. So just to make a very simple example in practice, this is the target function that I was mentioning before. So the main thing that you have to do when you write an application that wants to use libfuzzer is create a function that is called like that and implement the processing of the data. Because anytime that the function is called, and this again happens repeatedly over and over, feeds you with that data that you can access via that pointer there, which is exactly that size bytes, which means that this process data function that here is generic, here must contain all of the steps that you need to do in order to actually process the packets that you are receiving. Once you're done, you return, you receive a new packet, you do this forever and ever until you stop, or until it crashes, of course. And the idea is that you need to compile it using Clang again with some flags that actually help address some things, so like address sanitizer and stuff. Most importantly, the fuzzer keyword there that instructs Clang to actually involve libfuzzer. And once the application has been built, you just execute it with the folder to the corpus directory. As we'll see later, the corpus is basically the list of seeds that you want to start from. Because, again, if I'm testing RTCP packets, I'm not just feeding random data to the application. I mean, I may do that just to see if it's robust enough, but typically what I want to do is take existing RTCP packets, mess with them enough so that they are pretty much confused, and then feed them to the application. And so having valid RTP packets in there actually helps the fuzzer do something that is actually more aware of what you are trying to investigate. But most importantly, you can also pass another parameter to the fuzzer. So if you pass a specific packet here instead, it will not do the whole iteration that we've seen before. So it will not iterate forever for that function. It will just pass that exact packet to that target function that we see, and then will exit, which is really helpful whenever you need to re-replicate a crash that you experience. So you got a crash for some reason, the libfuzzer will actually dump the actual packet that crashed your application to the disk. which means that then you can actually inspect that packet. You can inspect it via some other tools. You can inspect it via a hex application or so on. Or you can just feed it again to your application, maybe after some fixes, pass it to GDB in order to investigate exactly what crashed and so on and so forth. It's really just very helpful in order to figure out how to fix your problem so that next time you iterate, it shouldn't happen anymore, at least for that kind of bug over there. Which brings us to how we actually integrated all of this in Janus. So first of all, we needed to add support for CLang, which wasn't actually very troublesome for us. I mean, normally we just built with GCC, but it built just fine with CLang. But still, we got some warnings out of the CLang compilation that were actually some red flags. So they spotted some things that we were doing incorrectly that we fixed. So it was a nice added value for that. And the next point was, of course, choosing what to fuzz. Because as I was saying, we cannot just, let's say, take all Janus and pass it to libfuzzer. We need to select exactly what we need to investigate and focus on something specifically. And we decided to start with RTCP, which meant isolating the functions that we use for parsing RTCP specifically. So all the functions that we involve anytime that we receive an RTCP packet and we start doing some things with that. And RTCP was actually a very good starting point because it's actually one of the most likely packets to crash your infrastructure, just because of the compound packets which might have length values in there, packets like NACS and so on that rely a lot on loops and a list of information in there that cause you to iterate a lot on the packet and so may cause infinite loops and stuff like this. So I put the fun there in quotes for a reason because it was actually quite problematic to solve everything, but it turned out to be an interesting experience. And then, of course, we needed to work on the libfuzzer workflow in general. So again, we isolated some of the critical RTCP-related functions, and then we had to write a couple of scripts to, first of all, build the fuzzer in order to build everything that we needed to do and in a way that was compliant with libfuzzer, and some scripts in order to run these in an automated way, so something that we could automate somehow. And all of these ended up into a pull request that we wrote for our project. This pull request has since been merged by Alessandro. Actually, we added some other stuff like RTP and SDP, partly SDP fuzzing support as well. But it's still an interesting read if you want to learn a bit more, especially in terms of what we needed to change, for instance, in the make file for this to work, what we needed to do in the scripts and so on. And just to give you a very small snippet of the same target function that we saw before, but specific for Janus and specific for RTCP, you can see that we are just using some parts of the Janus code. More specifically, we are including the header that includes all the RTCP-related stuff. And then we treat the incoming data as if it were an RTCP packet. So first of all, and this is something that we already have in the code now, we check if this packet is actually an RTCP packet, which means making this function robust enough that we are sure, first of all, that we are not passing anything that doesn't even look like RTCP to our functions below. And this was a very important step. And then basically, you do everything else that typically you do with RTCP packets, that in our case involved some context. Here it's an example of how you can look for a list of NACs, the NACs that Matthew introduced in his presentation before. So inspecting an existing RTCP packet, see if you can find a list of NACs, and if there are any, free the list, and so on. And something that I forgot to say, once you're done with all of these and it didn't crash and everything worked, it's very important that you free all the resources you allocated over here, because the libfuzzer is also very strict in its leak sanitizer support. The moment it detects a leak, it crashes. And it does this for a reason, because it means that if it's going to do a million iterations like this, and every time you leak something, you know for sure that eventually it's going to break for one reason or another. So just because you exhaust the memory or something like this. So making sure that you fix your leaks before you worry about anything else is actually of paramount importance. And we actually had, it was very helpful for us. As I was saying, the code coverage is important as well, and libfuzzer gives this to you for free, basically, if you use the right flags. And in this example, you see which parts of the RTCP.c code was covered, for instance. So we didn't cover these lines here at all because it never happened that the length was shorter than the actual length of the We never got some packet that was small enough to fall in here, or some packet that was small enough that it didn't fit the header length of the RMP packet, but you see that other lines instead were covered a lot. So for instance, checking a sanity check on the RTCP packet length and stuff like this. So doing this on a regular basis and evaluating your coverage guide, your coverage in general is very helpful for this. And I was mentioning corpus files before, so the fact that you actually do need a list of valid packets for your protocols to start from. And the way we started was basically just reusing the ones that Chrome had for their own fuzzing part. So they had a lot of packets there to start from. We reused exactly the same, and it was quite useful. But of course, this gives you a limited coverage because it basically covers just what the Chrome guys provided as part of a subset of RTCP protocols, packets, and so on. While it might make sense to try and provide even more packets to that, so something that covers packets that address maybe some parts of the coverage that we've seen before that you don't cover too much. And for this, actually, together with Iñaki from Meetecho, we created a new repo that is supposed to be, let's say, a shared repository for corpus files. So at the moment, we only contributed some files that we provided ourselves to the community, and the same did Iñaki. But the idea is that supposedly this should help the whole RTC community. So all of the applications that are interested in taking advantage of fuzzing one way or the other, the idea is that everybody contributes what crashed them so that basically it can help figure out if the same thing happens to us as well with the same input that caused theirs to break, basically. So it's an attempt to provide a community effort for this, and I hope that if you start addressing fuzzing as well in your application, you'll take this into account and contribute. One last thing before I actually complete is scalable distributed fuzzing via OSS Fuzz, because what I described so far is basically something that you do in an application that, in a framework that you control. It can be your laptop or one of your servers or whatever. The nice thing, though, is that Google provides a distributed fuzzing via a project called OSS Fuzz, where you basically provide a script to basically install your stuff, and if accepted, they basically do the same thing on a much larger scale on their own cloud infrastructure, which is, of course, a hugely helpful approach, because then you can take advantage of the whole Google infrastructure to fuzz your to fuzz your application continuously, regularly pull updates, and so on. And most importantly, of course, they notify anytime a crash comes. And of course, I just got 2 notifications a few days ago, so something that I have to come back to have a look at as soon as I come back to Napoli in a few days, but hopefully nothing major. But again, this shows how actually without doing anything, fuzzing was already helping me figuring out something that is wrong and that I need to fix. And the process was actually quite easy. All you need to do is write the scripts in order to integrate with OSS Fuzz and submit a pull request so that it's part of their project. So I suggest you do that as well in case you are thinking about that, mostly because it provides some very useful information. So in this case, it does provide you with 4 different approaches to fuzz testing. And funnily enough, it also includes the American fuzzy loop. So it uses American AFL as well for fuzzing, even though it's not part of our own fuzzing scripts, which is a nice added value. And then it covers stuff like memory sanitizers, leak sanitizers, and all of that independently. So you can actually address these things in a separate way. And to read the blog post that is written much better than the way that I just explained it, you can just head here to the WebRTC hacks blog post, because this is the blog post that Alessandro wrote that is probably, I don't know, 10 or 12 pages long if you have a look at it as a document. He explains in real detail all of the steps that I tried to summarize here. So it's really a very good starting point if you want to start trying to do the same thing in your own infrastructure, because it goes really into all the nitty and gritty details of what you need to do, what needs fixing, what actually broke our application, and so on. So about the next steps, I mean, we focused a lot on RTP, RTCP, and again, I say in part SDP because it's not currently very aware of structure. We are just messing with strings a bit. It's still effective, but not as much as I'd like to. And for these, I'll probably come back to Henning and Sandro's presentation for more feedback on that. But in general, we want to have a look about transports in general in order to make sure that a generic signaling message doesn't crash our application, or at least it shouldn't do that. we want to expand the corpora that I introduced before. So hopefully more people will contribute to that project that I introduced. But of course, libfuzzer was one of the options. It was the option that was most effective and familiar for us, but there are others out there. And again, Henning and Sandro introduced many last year. There may be tools that we might use for black box testing as well. So it's definitely something that we want to investigate. So that's pretty much all. So before coming to questions, I just want to make a very brief announcement. So we are going to host our own conference on Janus in a few months. So you can think of it as the Kamailio world of Janus, basically, because I'm trying to learn a lot from what Daniel and the community have done here. I mean, I love the spirit that the developers and the community exchange at the events like this, and I really want to try and benefit from the same thing for Janus. So if Janus is something that interests you, I mean, just head to the website over there. It's going to happen towards the end of September. And I also want to take the opportunity to give a big shout out to Fred over there. Fred Bosner was the first sponsor of our event. I mean, from the first day he said, I won't be able to be there for personal reasons, but I still want to help you and support you. And for this, we'll be forever grateful. I mean, you got to love the guy for that. And that concludes it. So if you have any questions on this, I mean, please let me know. And of course, I'll be here for the next couple of days. So in case you have any questions on this or on the event, feel free to stop me and ask me anything. Thanks.
Thank you. So, questions? Here, Tim.
Do you know if anyone's done any fuzzing on Opus?
Not that I know of. I mean, so far, most of the RTP fuzzing that we did was on video, mostly because in video, we typically have those payload descriptors that can actually cause issues like that. So inspecting, for instance, resolution or the temporal layers or stuff like this, payload descriptors like VP8, VP9, H.264s, and things like this. For Opus, we never really need to inspect the packets ourselves, so it's not something that would break us directly. So it may be something that end-to-end can cause issues, because we typically don't decode Opus directly. We typically just access the RTP extension for input levels, for instance. But RTP extensions are part of the things that we did fuzzing for, because it's one of the things that you need to be prepared for actually boundary-defined protocols and so on. So something that we needed to investigate.
If the question was about Opus as the library, it has been extensively fuzzed, and from time to time, new security issues are found, but they are being found using fuzzing by other people. Yeah, probably using OSS fuzz.
So good news. It means that I don't have to do anything there then.
Okay, so we have Lorenzo here. Please approach him for further questions, especially about that VoIP on the beach, which is actually with some pizza around.
Yeah, a lot of pizza, Jay. I should have said that. That's the very first thing.
But now we are moving and we try to keep the same speed. Thank you.